Hi, Vicky. I'm so sleepy. Let's start in like 5 minutes, right? Let's start at 11:36. Have out the homework and open up the Phet simulation. We are going to be working together on the Phet simulation. We're going to be doing stuff at the same time. What I really wanted was to screen share and show you like what I wanted to show you on the simulation. But since I can't get the screen share to work, we're all gonna be on the same simulation together. Hey, Isabel. So let's all go on the simulation together. So I have that opened up. I'm just reading through some of your responses. Good morning. Why don't we, Vicky, we're not allowed to use Zoom. Otherwise I would. Then I would like to use Google Meets because then we can do a screen share through Google Meets. But the problem with Google Meets is that I can't record the meeting, and students who aren't tuning in at 11:30 would be unable to see. So I gotta do it this way. So for those of us just joining us in the chat, please open up the Phet simulation, waves on a string. A large part of this lesson will be you on that and not even looking at the stream. You're just going to be listening to me. Yeah, I'm going to go ahead and use the restroom, and we can start in 2 minutes right at 11:36. Okay? Yeah, so please open up the simulation. All right, well, Aaron, okay. Obviously, I'm not tech savvy enough to do that. I just you're banned. You're banned. I'll be back. Laura, Aiden. Aiden, I'm trying. Do you want to get banned too? Huh? Aaron, I'm just kidding. By the way, I hope you know I was just kidding and banning you. I wanted to time you out only for like a minute, but it's timing you out for 5 minutes. I'm so sorry. Aiden, I don't know how to do this screen record. I've tried on the thing and it's not, you know, on the stream, it's not really letting me do that. So, but I think this method has its advantages. Like you get to actually do it yourself too. Okay. So I am going to, let's all go to the simulation. All right. And I think if you do it, if you open it in a new window and have this chat stream on the other, you can kind of make it so you can look at the chat and the simulation at the same time. So please, make it so that, that's possible. All right. And here we go. So we're on a simulation now. And I want to go over your responses. Okay. So here we go. Number 1 says play around, shake it up and down, make big pulses, small ones, blah, blah, blah. What's the one thing that always remains consistent about the waves? The one thing that always remains consistent is like the shape of the wave. Like when you send it, like the shape as it travels from left to right is always just going to be that way. If you have some damping going on, then the amplitude of that wave gradually does decrease. Okay. Excuse me. The other thing that remains consistent is the speed. No matter like what you do to the wave, the speed that you send it through will always be consistent. Okay. So you should have noticed that, and the only thing you can really do to change the speed is change the tension. There's nothing you can really do about like how you shake it that's going to change the tension of this, that's going to change the speed. And you should have noticed that as you increase the tension, that the wave speed increases, and if you decrease the tension, it should decrease. It's not a linear relationship, it's actually a square root relationship, but that's not a formula that's kind of vital to know, right? So now we can change the frequency. And you should have noticed the higher you change your frequency, and you can do this now, right? If it's on oscillate mode. When you increase the frequency, the wavelength decreases. When you decrease the frequency, you should see the wavelength increases. And the formula that justifies this is V equals lambda times frequency. The speed of the wave equals the wavelength multiplied by the frequency. And I hope that playing around on the simulation made that formula like a lot more relatable. But the one thing that you should have noticed, and you needed to have included in your response when I'm checking these answers, is that relationship, that big lambda corresponds with small frequency, and small lambda corresponds with like big frequency, is only true if V is constant. You needed to have included that in your explanation. Okay, and it's only true because V is constant. Because why? As I change the frequency and observe the change in wavelength, I'm never like altering the tension, right? That was a big no-no. If you actually like use the ruler and stuff, you should have gotten a speed around 6 or 6.5 meters per centimeters per second, or 0.06 meters per second. Right? Depending on how you measure it, it's just going to vary from blah, blah, blah. All right. Now, something is going to be, we're going to do a fixed end and oscillating mode. All right. So everyone, your oscillation should have, so what you should have noticed about the wave is that when it's reflected, the amplitude stays the same, the speed stays the same. There's 3 observations. 1, the amplitude is the same, the speed is the same, and it's upside down. Those are your 3 big observations, okay? This is on manual mode, right? Any pulse that you send, when it gets reflected, the speed's the same when it returns, the amplitude's the same when it returns, but it's just upside down, right? A lot of us manage to observe all 3 of those things. That's really nice. Now, that was really simple because it was just like one pulse that's like reflected over and over and over again, right? But the more interesting thing is if you send one bump, but if you send like a wave periodically, into the thing. All right. So a lot of you wrote observations down like when the wave interacts with thin reflection, the amplitude and the wave height increases. It also flips over the x-axis while maintaining the same wavelength and speed. Stuff like that is true. Here's what I want you guys to do. I want you to set your frequency to be 0.41 hertz and your amplitude to be 0.01 centimeters. Okay, I'll write this down in the chat. Okay, so amplitude is 0.01 meters. Frequency is 0.41 hertz. Tension is highest on high is highest setting. And there is no damping. Okay, make sure there's no damping here. Okay. All right. And I want you to press play. Oh yes, 0.01 centimeters. This. This is super small. And it gets bigger. What you should see is that it gets bigger and bigger and bigger and bigger and bigger. Okay? Why does it get bigger and bigger and bigger and bigger? Because you're basically sending a tiny 0.01 centimeter wave over and over and over again towards the right. And that gets reflected and reflected over and over again. And you keep adding a 0.1 centimeter wave. So it gets bigger and bigger and bigger. And that's essentially what's happening here. Okay? Now, what I want you to do is to press reset, click restart, and double the frequency to 0.82 while keeping everything else the same. Press pause, restart, frequency is 0.82, 0.82, and press play this time and see what happens. Something cool should happen. I think it's pretty cool. You get a really nice stable pattern with a point directly in the middle of the rope that's not moving at all, and two humps that all go up and down, right? Type in the chat, is that what you're seeing? Yes or no? Okay. I just want to make sure we're all on the same page. Yeah, awesome. It's dancing, exactly. Okay, now I want us to go to 1.43. And if you can kind of guess the oh, no, 1.46. 1.46 hertz. Reset it, pause it, all right, and then press play again. Okay. Go to 1.46. And the numbers we should have done before were 0.42, 0.84, and now we're doing 1.46, okay? Oh, 1.26. Well, I'm so sorry. 1.26, yikes. So again, the first frequency was 0.42 hertz. The next was 0.84 hertz. And then this one is 1.26 hertz, right? And you'll see that the interference pattern that we're creating now has 4 points where there's no movement at all, right? What? There's only 2. Look at the bookends. The bookends count 2, right? And there's 3 dancing humps now, right? Can someone guess in the chat what the next frequency is going to be that's going to create 4 humps that are dancing? What would that be? What would that frequency be? Someone put it in the chat, please. Close, Josephine. It is 1.68, okay? Exactly. So everyone put in 1.68 as the frequency now and restart it. After you put 1.68, let's restart the simulation and see if we get 4 humps this time with 5 points that don't move. Oh, super cool. Isn't that super cool? I've always thought this was super cool. Okay, and lastly, let's do the next one, which would be 2.1 hertz. No, is it 2.2? Yeah, it's 2.2 hertz. So let's do 2.2 hertz. That's our last one. Okay. No, it's 2.1. It's 2.1, 2.1 hertz. Sorry. 2.1 hertz. And here we have, yes, 1, 2, 3, 4, 5 humps. Okay. All right. So while that simulation is still running, all right, I want it to be always running so you can reference it while we go over the rest of the lesson. So now the rest of the stream will be on the whiteboard, so you can turn your attention back to the regular stream. Okay? And Alon pointed out something really cool, 2.52 hertz, like the next frequency that works, will actually have all the green dots not moving at all. Okay, there's a special term for what those dots are. They're called nodes. For those of you who have done a little bit of reading beforehand, you'll know what I'm talking about. Okay, just hold up for a second. I'm really hungry. I just need some crackers. Okay, cool. So if we could all go back, bring our attention back to the stream, not your simulation. what we have essentially gone over and introduced ourselves is a thing called a standing wave. And it's called a standing wave because it looks like there's no horizontal movement, right? All I see is like stuff going up and down and up and down, and there's no like side-to-side movement of the wave. So the wave, so we'll call this the first mode. In the first mode, the string oscillates from this position to this position, right? That's all it does. And it doesn't look like there's a wave going side to side. Hint, there is. We're going to go over that in a bit more detail too. Okay? So the second mode oscillates from this position to this position, right? At one moment it's like this, and the other moment it's like that, right? No big deal. It's like a chicken or egg problem. Like one doesn't occur first. It's just like it'll always oscillate between those two positions, okay? The third mode looks like this. Right, it'll oscillate between those two positions. The fourth mode looks like this. Right, and I'm not even going to draw the fifth mode, right? But you can kind of, fine, I'll draw it. I'll draw it just for you guys, okay? Right, that's what the fifth mode looks like. All right, these have alternate names. This is frequently called the fundamental. And then this is called, in music, the first harmonic. And this is the second harmonic. And this is the third harmonic. Vice versa. That'll be the fourth harmonic, right? I want us to look at the anatomy of these standing waves. There are really special points in a standing wave. Some of you have already like noted like what these are. There are points that never move, right? There are molecules in my standing wave. If you go back to your simulation, right, you can kind of see like which ones are like never moving, right? They kind of evenly split up the whole wave in itself, right? And and if you turn your attention back to me on the screen, all right? These points are called nodes, all right? I will abbreviate them with the letter N on my diagram here. So I have a node here and a node here, okay? In my second mode, I have a node here, a node here, and a node here. Like that point never moves up and down, right? Like I could go, if I saw that standing wave in real life, I could just go and put my finger there and it really wouldn't even interfere with the wave at all because that point's never moving. All right, my third mode, I have a node here, a node here, a node here, and a node here. My fourth mode, I have a node here, and a node here, and a node here, and a node here. And my fifth, for n equals 5, I have a node, 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 node. If you notice, the pattern would be for your nth mode, you'll have n plus 1 nodes, right? Conversely, there's a location on every standing wave called an antinode, and it's the exact opposite. It's every other point besides the nodes has some movement, right? The points where the particle moves the most is called an antinode. So there's an antinode here, right? This particle moves the most out of all the particles in the string, right? This particle only goes like this much, but this particle here goes that much, right? So we call it an antinode. And I have an antinode here and an antinode here. I have an antinode, antinode, antinode here. I have an antinode, 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 antinode here. And I have an antinode, 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 antinode here. Right? What's the rule here? The nth mode has n number of antinodes, right? Excuse me. Oh, that's good. Okay. I want us to now think about the wavelength of the wave we're generating that causes these standing waves, right? And I want us to relate it to the length of the actual string. So if my string is this long, what's the wavelength of this first mode? I would argue that it is twice the length of the string. Why? Because the whole wave is that big, right? And that's twice the length of the string. The second mode, its wavelength is just L. It's contained, the whole wave is in the string, right? The third wave, its wave is 2/3 L. Because if I look at one complete cycle, this is 2/3 of the length of the string, right? It's 2 humps out of 3, right? This one, its wavelength is half the length of the string. And for the fifth harmonic, this is 2/5 of the string, right? So it would be 2L/5. For those of us doing sequences and patterns in math, can you type in the chat what the formula is for the wavelength in terms of n for the nth mode of vibration? In terms of L and N, what would the formula for my wavelength be? And your general formula, remember, should be true for all 5 of these. Can I see it in the chat, please? I'm excited to see. 2L/N. Exactly, right? And it requires some clever thing. Oh, of course, this is 2L/2. Oh, of course, this is 2L/4, right? And that kind of helps make the whole thing make more sense. So basically, you'll notice that each mode of vibration, all you do is you take the fundamental length and you half it, you third it, you fourth it, you fifth it. And that's how you get the frequencies too. You double it, you triple it, you quadruple it, you quintuple it. And that's why our allowed frequencies of vibration in our initial exploration were 0.42, 0.84, 1.26, 1.68, because you're just multiplying 0.42, you're just finding the multiples of that. And why are those the only allowed frequencies that produce standing waves? If you chose any other frequencies but besides those, you'll find it doesn't work. Because those frequencies that you found are the things that correspond to 2L/N, right? Because if V equals frequency times lambda, and this is 2L over n. Okay? Your allowed frequencies are the speed of the wave over 2L times n, right? So all you got to do is multiply the fundamental one by 2, 3, 4, 5, 6, 7, 8, 9, right? And those are your overtone series. That's like your harmonic series. Okay. Cool. Any questions so far? A lot. If it's not straightened out, it just doesn't create a standing wave. We just wouldn't call that a standing wave, right? It's just like a flat line, like it doesn't do anything. All right. So you're gonna have a really short. You know what? I know this week's a little weird. A lot of you are preparing for APs and stuff. There won't be an assignment today. Except to watch a video. I'm just going to give you a video to watch, and I'll give you like 1 or 2 questions about it to answer, and that's it. It's like really, it should take 5 minutes, right, to do. And we'll end our lecture on that. So standing waves are really important because these are essentially how musical instruments work. And we're going to go over the connection to music later in the week. But tomorrow we're going to go over exactly how these form. Like, why are there nodes? Why are there antinodes? Why does it appear just to go up and down? Because we know what is really generating this. It's a wave that's going to the right, and its reflection that goes to the left, and their superposition and their interference causes the standing wave, right? If you do the simulation again, but do a loose end, so the string goes out the window, you will not be able to form a standing wave. The standing wave will only form because there's a reflection. So even though it appears it's standing, there's actually a lot of horizontal movement going here. There's a wave traveling to the right and a wave traveling to the left, and you just can't see that here. But you will be able to see it in the video I'm going to send you. So get pumped about that. And I'll see you tomorrow where we're going to discuss the video and exactly how standing waves form from the interference of a wave in its own reflection. All right? So with that, I'll bid you adieu and have a great day. Happy Tuesday. Okay?